Broadcast is now starting. All attendees are in listen-only mode.
Good day, everyone. Welcome to the June Pacific Northwest Drought Early Warning System Drought and Climate Outlook webinar. My name is Holly Prendeville, and I am the coordinator for the Northwest Climate Hub. This bi-monthly webinar series is hosted by NIDIS, the Northwest Climate Hub, and ACRI. It's designed to provide stakeholders and other interested parties in the Pacific Northwest with timely drought and climate information. Each webinar will be tailored to reflect recent, current, and forecasted conditions and climatic events, but will also include discussions of observed impacts and other relevant updates from across the region. Webinars and recordings and other supporting material will be posted on drought.gov later this week. Also, for those of you on the live broadcast, after the webinar, you'll have an opportunity to provide feedback to help us improve this webinar series. So please take a moment and let us know what you think. Next slide, please. Today's speakers include Larry O'Neill with Oregon Climate Service, who will give us a climate recap and current conditions. Then Troy Lindquist from the National Weather Service Weather Forecast Office in Boise will give us a seasonal conditions and climate outlook. Then we'll hear from Brian Potter with the Forest Service Pacific Northwest Research Station about long-term drought effects on fire in the Northwest, what we know and don't know. And then finally, we'll hear from John Abatsaglu at the University of California, Merced, about compound extremes driving the Western Oregon wildfires from September 2020. Next slide, please. Before we begin with the presentations, we wanted to highlight the partners who make this webinar series possible. The Northwest Climate Hub develops and delivers science-based, region-specific technologies and practical information that will assist agricultural and natural resource managers with climate-informed decision-making in Idaho, Washington, Oregon, and Alaska. You can go to the website to get more information. Next slide, please. ACRI, the Oregon Climate Change Research Institute, is a network of dozens of researchers in Oregon's public universities that work closely with other public and private entities. ACRI is housed at the Oregon State University and advances understanding in regional climate impacts and adaptation and cultivates climate-informed communities. Again, their website is located at the bottom of the page. Next page, please. NIDIS, the National Integrated Drought Information System, was established in 2006 by public law with a mission to improve the nation's capacity to proactively manage drought-related risks by providing those affected with the best available information and resources to assess the potential for drought and to better prepare for, mitigate, and respond to the effects of drought. NIDIS is building the foundation of a national drought early warning system through the development of regional DEWS, where networks of partners and stakeholders share information and actions that will help communities cope with drought. While the ultimate goal of this national early warning system, we recognize that impacts and early warning information differ across the region. Each DEWS has the same base ingredients, but ultimately their own flavor to reflect the needs of their region. The PNW DEWS was officially launched in February 2016, and the strategic plan and information on current activities is available on drought.gov. Next slide, please. COCORAS, the Community Collaborative Rain, Hail, and Snow Network. We use COCORAS to help facilitate our early warning system with more precipitation observations are needed. We encourage you to join COCORAS. This is a unique nonprofit community-based network of volunteers of all ages and backgrounds working together to measure and map precipitation, whether that be rain, hail, or snow, as well as condition reporting. Observations by COCORAS observers and precipitation events and the lack of precipitation events are important to capture and improve our understanding of weather. As COCORAS says, be a hero and record those zeros. We need to understand where there is no precipitation occurring, particularly now in this drought. To become a volunteer or learn more, visit cocoras.org or contact your state coordinator, and we'll enter those in the chat in a bit. Next slide, please. Some news from the PNW DEWS. There's a new fact sheet, a how-to video to help users learn how to use Seymour drought surveys. First, when you go to the National Drought Mitigation Center, you can report the Seymour drought surveys, and with this video, I'll step you through how to do that, the best learned practices, and how to access social media and fact sheets to recruit new users. The website's at the bottom, go.unl.edu/CMOR_drought. Next slide. We've had some requests of folks wanting to know where they can find federal drought declarations. The USDA, the Department of Agriculture's Farm Service Agency, has a disaster drought designation information website. We'll put this link in the chat box in a moment. This is where you can find that information. And next slide, please. I will show this again at the end of the webinar, but just want to make sure to let you know we're going to give you everybody's email addresses and then to mark your calendars now for the 23rd of August for the next webinar. We'll now turn it over to Larry O'Neill, who will give us our recap of the latest climate conditions. Larry O'Neill is at the Oregon Climate Services, the state climatologist. Larry.
Thank you, Holly. Well, good day, everyone. So today I'm going to give a brief update on current conditions for spring 2021 and some of the impacts that we're observing. So the first thing I want to talk about is the unprecedented Pacific Northwest heat wave. So this is just a visible image from the geostationary satellite, and this was yesterday. And one of the very rare times that you will see the entire Pacific Northwest DEWS region completely cloud-free. So we set a lot of records as maybe most of you are aware of, and it is contributing to deteriorating drought conditions as well. I just want to list a couple of the significant weather events or events that we've experienced in the Pacific Northwest during this springtime. So the first thing is probably the most significant one is this was the second driest spring on record for the Pacific Northwest in terms of precipitation. And this is hastening an already serious drought situation in many parts of the state, in many parts of the Pacific Northwest. We had early snow meltouts in various places, most significantly in the southern and central Oregon Cascades, but also other places as well. We are now experiencing an unprecedented Pacific Northwest heat wave. So these temperatures that we've experienced and are currently projected to experience the next few days have not been recorded before in our historical conditions. We have significantly deteriorating drought conditions throughout the region, and this has led to very severe impacts in all three states, Washington, Oregon, Idaho, and western Montana as well. We've had early arrival of monsoon thunderstorms in eastern Oregon and Idaho, and so this is a concern for wildfire potential as we get a lot more lightning strikes out in the wilderness. And finally, a significant event is we had a atmospheric river event in June that was abnormally strong for this time of year, and it impacted mainly western Washington and western Oregon and kind of missed out the rest of the region. Although it did provide some beneficial rainfall to these regions, it didn't really change the trajectory of our drought significantly. So this is just a map showing the yesterday temperature records that were set during the heat wave. So all these black X's, so this animation goes by hour of the day, and it just shows you when various records were set. And you'll notice that the black X here are either tying or breaking all-time record high temperatures within the region. So we had many locations within both Oregon and Washington, particularly Western Oregon and Washington, that broke all-time records yesterday. And then the pink and other colored dots show either monthly or daily record high temperatures being broken as well. So that's expected to continue and start to move east towards Western Washington and Oregon and into Idaho. So you'll all get your day in the sun for breaking temperature records as well. And unfortunately, this heat wave is projected to continue for quite some time. And Portland recorded 112 degree Fahrenheit temperature. So it broke its all-time high by about 3 or 4 degrees Fahrenheit. And this was a nice map I saw this morning that just puts this sort of very warm temperature reading into context. So these are stations within the country that have ever been warmer than Portland's 112 degrees. And so you see a lot of these stations are either in the desert Southwest in California or kind of in the Midwest with a few stations in Western Washington as well. So this is just very unusual conditions for this part of the state, Western Oregon and Washington, and kind of puts it into context with kind of how unusual the event was. So some impacts on Western Washington and Oregon. So we just generally don't experience this sort of heat, and so this was just a nice example showing that the heat got the road so hot that they cracked pavement and other, in a variety of places around Western Washington. This was pretty unusual. So what's causing all this? So it's the heat dome, what's called the heat dome, and it's this basically high pressure center that centered itself over Washington, Oregon, and British Columbia, and this is forcing off downslope flow and subsidence warming within the core of the high pressure system. And so this is high pressure pattern is very similar to other historical Pacific Northwest heat waves. So this is a nice paper showing a composite pattern from a paper by Karen Bambako and colleagues in 2013, showing that all Pacific Northwest heat waves had this high pressure center in common that was centered kind of in British Columbia. And the difference with this one and why this is so intense is that the high pressure center is much more intense than it has been in the historical data record. And I just want to shout out to this really nice paper I found very useful the last week. It's History of Pacific Northwest Heat Waves. This was in 2013, and it shows a really nice, very nice summary of all of our past heat waves up to 2013. And I was talking with Kathy recently, Kathy Dillo, and she said that this paper is going to need updated given the current heat wave and then the one we experienced in 2017 or something like that. But a lot of historical context still holds for this. So here's a DOI here, and I can put it in the chat later if anyone's interested. This is a really nice paper to read. So switching over to just the kind of the conditions during the springtime, I like to start with the U.S. Drought Monitor progression through the season, because this gives a good idea of what temperature and precipitation patterns, anomalous temperature and precipitation patterns. So the figure on the right here just shows the beginning of May, what the U.S. Drought Monitor showed, and it showed much of the Pacific Northwest in some sort of either normally dry or drought condition. So these colors indicate the intensity of the droughts, with the progressively redder colors indicating progressively more severe drought conditions. What's concerning is these areas of D4, which is exceptional droughts in the Klamath, in and around Klamath and Lake counties, but then this big area of D3, which is severe drought. So the figure on the left shows where we're at June 22nd. So during the intervening time, the drought severity increased significantly, and also the drought extent. So now we have extreme drought conditions going into Western Washington and encroaching into northern Idaho. And then we had the addition of D4 drought in central Idaho, as well as we have historically dry conditions within this area. And basically everywhere in Oregon and Washington, the drought severity increased here. So the percentage of area in droughts, either moderate drought to exceptional droughts, is currently at about 79.8% compared to 61.5% at the beginning of May. So the part of the driver of this drought is just the extremely warm weather that we've had the last few days. And so this map is from the Climate Toolbox and shows the mean daily temperature anomaly over the last 90 days. And so this map is just all red. So this indicates that we've had warmer than normal weather on average over the last 90 days. And for the most part, the warmest weather was in southern Oregon and going up into central Washington as well. So the average, kind of for the region-wide average, we've been about 2 degrees Fahrenheit warmer over the last 90 days compared to the 1991 to 2020 mean that was just released. So comparing these temperature records to the temperature anomalies to historical records, we tend to look at what are called the percentiles of the temperature distribution. So this just says how often these temperatures have occurred in the historical data record. And for the most part, we're in the what's called the 90th percentile in much of the region. So much of southern Oregon, parts of southern and central Idaho, and eastern Washington have been above the 90th percentile, which just indicates that these temperatures are fairly infrequent in the data record. And then if you just go to the last 7 days, up to and including Saturday, we're experienced, the last 7 days have been historically warm. So any of these dark red regions indicate the highest 7-day temperatures in the historical data record here, spanning back to 1979. And then all the other areas in the Pacific Northwest practically have been above the 90th percentile in the last 70 days. So this has really been kind of a historically warm week here. Now moving on to precipitation. This is just a broad overview of the whole Pacific Basin, showing precipitation anomalies for March, April, May. And this just shows the percent of average here. So we can see all of the Western North America, going down into Mexico, going up through California, into the Pacific Northwest, has been extremely dry in terms of precipitation, and really so has the whole Eastern Pacific, Northeast Pacific here as well. So this gives a little bit of broader context that we're kind of in this pattern of just large-scale precipitation and circulation anomalies here. Now, if we zoom into the Pacific Northwest, the last 90 days have been extremely dry, and we've only received much of, especially eastern Washington and parts of northern Idaho and southern Idaho have only received less than 30% of their average precipitation during the springtime. And then also large parts of Oregon as well have been well below normal here. And so if we just look at the historical data record, where does this precipitation anomalies rank? So in Washington, Oregon, Idaho, this has been the second driest March, April, May on record, and these records span back 127 years to 1895 here. And so, so it's been just a really unusual spring for us. If we just look at, instead of the 3-month, we just look at how our water year 2021 is looking like. Right now, Idaho ranks at as the 11th driest water year, going back to 1895, 1896. Oregon's at its 16th driest, and Washington's at its 45th driest. I should note that the Washington figure is kind of weighted more by the heavier precipitation that's fallen in the Washington Cascades in western Washington, but that the eastern Washington has been about as dry as Idaho and Oregon have been. And just for drought monitoring purposes, this drought is a multi-year drought that we're experiencing. And so this really goes back to precipitation deficits that have built up over the last 2 years or 2 water years. And so if you look at the 24 months rankings, Oregon's at its 6th driest 2-year period, Idaho is at its 8th driest, and Washington's 46th driest on record. The Oregon's, so the snowpack has, I'm just going to point out for time constraints, the Oregon Cascades evolution. So our snowpack has got to normal to slightly above normal in many basins at our April 1st snowpack peak, but has since melted out much earlier than normal. So melt out of the Oregon basins occurred about 1 to 4 weeks earlier this year than normal. So stream flows have also been very concerning for the Pacific Northwest in general. So this is a current map showing all the USGS stream gauges in the Pacific Northwest. And what I want to point out is all the red, the bright red and brown dots. So this indicates stream flows that are well below normal, or in the case of the bright red dots, historical lows for the state. So the big regions are in central Idaho, problem regions, central Idaho, parts of western Washington, and then much of western Oregon, in both the coastal mountains and the Oregon Cascades. And then also out here in the John Day and off the Willows as well. And so we could look at just the time series of stream flow percentiles that are aggregated by state and just show the progression during the last 2 months of stream flows. So we could see that at least 70% of Oregon streamflow sites and about 70% of Idaho streamflow sites have been below normal, and about 40% of both Oregon and Idaho have been much below normal. So it's this drought is severe. So this would indicate severe drought. Washington is faring a little bit better, in large part due to the above normal snowpack they got and the not so rapid meltouts they've experienced during the spring. The lack of precipitation and warm temperatures have substantially dried out soil moisture in the region, and this just shows the soil moisture percentiles over the Pacific Northwest, valid as of yesterday. Everything in the dark red is historically low soil moisture content in the surface soil moisture, and so this is in the top about 4 centimeters or 4 centimeters of the, or 10 centimeters or 4 inches of the soil column. And so much of northern Idaho, much of Oregon, and then a lot of eastern Washington, central and eastern Washington are experiencing historically dry soil conditions. So this is a concern for both agriculture. We're seeing lots of impacts in both agriculture and livestock production, the occurrence of dust storms, pest infestations, and poor crop conditions in many of these regions. So I just want to summarize my key points. So Idaho, Oregon, Washington recorded second driest spring. We've had worsening drought conditions across the entire Pacific Northwest, and this drought is becoming, in some places, historically unprecedented. We're currently also experiencing an unprecedented heat wave. And I want to point out again these extremely dry soil moisture conditions, and this will affect both agriculture and fire danger going forward through the summer, as we don't expect any significant precipitation to remedy this. And the last point, I hope it's not too depressing, but the entire Pacific Northwest is drier now than it was at this point last year. So thank you very much.
Thank you very much, Larry, for your presentation and all of that information. If folks have questions for Larry, you can put them into the question box and we will get to them at the end of all of the presentations. Next, we'll hear from Troy Lindquist, who will give us the seasonal conditions and climate outlook. Troy.
Okay, good morning or afternoon, everybody. Can you hear me okay?
Yes.
All right, perfect. Okay, I want to start off with just some key points here. First off, I'm going to spend a little bit of time talking about the current heat wave and dry conditions, and that's expected to continue through the 4th of July weekend. And next point, Climate Prediction Center's July through September outlook favors above normal temperatures and below normal precipitation for the entire Northwest region. Drought conditions are favored to persist across the Pacific Northwest through the summer. There are just a few spots that aren't considered drought now, but it looks like they will trend that way. And above normal significant wildland fire potential is expected for most of the Northwest, July, August, and September. And finally, just a couple of slides I'll show about ENSO. Currently neutral conditions, the ENSO state, and that's favored to continue through the summer, with chances of La Niña increasing as we move into the fall and the winter. Okay, my first slide here is the high temperature forecast for today. I already had an excellent summary on the current heat wave, but if you look at these temperatures, even west of the Cascades into the inland Northwest, working your way into the lower valleys of Idaho, just lots of triple-digit heat. Record-setting heat, historical, all-time records being set in some places. And as we already heard, it's you look at my map on the lower right there, it's just that extreme or anomalously strong upper level high that's been dominating the weather over the area. This is just going to continue for the next several days. So it's just a pretty incredible period of heat. Jumping ahead to Friday, our forecast high temperatures across the region. things are going to trend down, right along the Cascades westward. But east of the Cascades, we're still looking at 5, 6, 7 days of triple-digit heat. So this is definitely going to just increase or worsen the drought conditions across the region. And in the lower right, you see that most intense part of that upper level ridge is gradually going to start to shift off to the east, but we're still going to be under the influence of just very strong high pressure over the area. This slide here shows forecast temperatures for the next 5 days across portions of Oregon and Washington. This is from the Pendleton Weather Forecast Office. So for instance, if you look at Pendleton, the forecast for today, 113, tomorrow 115, and the records for those dates are these smaller numbers just below. So the record for today was 109 set back in 2015, 102 for tomorrow set back in 2008. So again, just the extreme heat. The map on the right shows National Weather Service excessive heat warnings all the way from parts of California, Nevada, up over the entire Northwest, parts of the Northern Rockies. And finally, from our local Boise Weather Forecast Office, again, the forecast taking us through 4th of July weekend. For Boise, the heat's not quite as intense as some of the areas in Washington and Oregon, but nonetheless, very several days of consecutive triple-digit heat. So it's going to be quite the week as far as temperatures and dryness goes. So for the next 7 days, don't expect much for precipitation, although it does look like we will get some of that southwest monsoon moisture to gradually work its way northward, kind of get circulated underneath that upper level ridge. It's going to bring some hit and miss thunderstorms to the area, it looks like, but anything that does develop, it's going to be high based. Expect very little rainfall from individual storms. It's probably going to be more of a fire weather problem than anything with high base storms, lightning, potentially starting fires, and gusty outflow winds increasing fire behavior. So if we move on to the 8 to 14 day outlook from the Climate Prediction Center, on the left we have our precipitation below normal. Precipitation favored across the entire Pacific Northwest, and on the right are strong probabilities of above normal temperatures during that 8 to 14 day period. Our 1 month outlook from the Climate Prediction Center for July, again, below normal precipitation is favored, the map on the left there, and except for right along the coast, probabilities lean pretty heavily for above normal temperatures for the month of July. Our 3 month outlook, August, September, and October, so the latter half of summer into the early part of the fall. Looks like we're equal chances for kind of the northwest half of our Idaho, Oregon, and Washington region, with below normal precipitation favored for most of Idaho. And our temperature map on the right, above normal temperatures are favored during that period. Our seasonal drought outlook, as we've already covered, the drought conditions pretty much everywhere over the Northwest and Northern Rockies, and we expect those drought conditions to persist or intensify, and areas that currently aren't considered in drought, we expect drought development to be likely over the next few months. So we'll look at our stream flow water supply numbers in the next few slides. This slide is showing our observed water year runoff percent of normal. So from October 1st of 2020 through June 27th of 2021, you can see the percent of normal, these browns and reds indicating well below normal runoff numbers during that period. So much of Eastern Oregon, a good chunk of Idaho, especially across the south, around 60% or less of our typical runoff volume during that period. if we move on to our water supply forecast as a percent of normal for the April through September runoff period, you can see a lot of browns and reds on this map. And so much of the area, around 50% or less normal, especially in the kind of the central mountains of Idaho or further south along the Snake Plain or areas, you can see around 30%, in some cases even around 12%. So very incredibly low runoff volumes. If you go along the Cascades, western Oregon, you can see numbers just very poor as well. If we look at those numbers in terms of ranking, you can see across much of the central mountains of Idaho, southern Idaho, along the Cascades in western Oregon, and up into parts of southwest Washington, we're in the top 10 lowest runoff volumes for the April through September forecast period. So very incredibly low numbers across the region. This is looking at 51 years of data that the Northwest River Forecast Center has. So very dry conditions. And just a comment or two about the reservoirs. Many of the reservoirs, they didn't fill. We know the snowpack was very poor, runoff was very early. So Bureau of Reclamation data here for Warm Springs Reservoir. This is on the Malheur project in eastern Oregon. You can see the dashed red line here is the average. The dashed green line was last year, and this solid blue line is where we are for the current year. You can see we didn't come anywhere close to our average peak in filling the Warm Springs Reservoir, and heavy irrigation demand is really drawing this system down much quicker than normal. So expect well below average carryover in many reservoirs as we move into the end of irrigation season in the fall and the beginning of the next water year. So it does not look good for carryover reservoir storage for the next year. Moving on to the wildland fire potential outlook from our predictive services. We have July, August, and September on here. You can see the reds. Those indicate above normal significant wildland fire potential. So pretty much all the area in July and August and September, you know, things just don't look good as far as the wildland fire potential goes. And ENSO summary, ENSO neutral conditions are present, so our equatorial sea surface temperatures are near average across most of the Pacific Ocean. And the image in the lower right, those are sea surface temperature anomalies. And you can see that Niño 3.4 region, that's main study area for the Climate Prediction Center, where they use that region to kind of put the ENSO conditions into context. And the anomalies there are within a half a degree or so in general of normal. So we have those ENSO neutral conditions. And if you look at the forecast models on this chart here, just about all of them are pretty much in that neutral envelope as we move through the summertime period, even into the next fall. But as we get into late next fall and next winter, some of the models are hinting that we could see La Niña conditions develop, which would be favorable for typically a cooler and wetter than normal winter over the Pacific Northwest, if that does occur. So we'll see if that happens. Hopefully it does, and may give us a better chance of at least normal wintertime snowpack. That's a long way off. And last slide here, just a summary slide again at the same points I pointed out at the beginning. And that's all I've got. Thank you.
Thank you very much for your presentation, Troy. Again, any questions for him, please put them in the question pods and we will get to them after we hear from the speakers. Next, we have Brian Potter with the Forest Service Pacific Northwest Research Station, who's going to let us know what we know and don't know about long-term drought effects of fire in the Northwest. We see your slides, Brian.
All right, and can you hear me?
Yes, we can.
All right. Thanks for inviting me to present today. And I want to start out by saying that I am a fire weather researcher. The majority of my work focuses on shorter term weather impacts on fire. A couple of recent projects led me to start looking into the impact of drought on wildfires. So I will say I am still learning this. I am not an expert. And actually, much of what I'm going to present today is a summary of some of the work that Dr. John Abadzoglu, who's presenting after me, has done. So I am completely open to John telling me that I was wrong in how I interpreted it. That said, if I can get my slide to advance. Okay. For my presentation today, I'm going to focus on drought for wildfires as any measure that reflects preceding cumulative moisture or its absence, as opposed to instantaneous measures. So a lot of the time with what I look at, it would be what's the vapor pressure deficit right now, or what is the relative humidity, or something like that. But I'm going to look primarily at things that are commonly used in the Pacific Northwest for fire weather or fire behavior and danger or potential indicators that do include some sort of cumulative preceding moisture. So those include 100-hour fuel moisture, 1,000-hour fuel moisture, and for those not familiar, those hours are a representation of the time that it would take for a fuel to move 2/3 of the way, basically, to the e-folding time for fuel moistures to reach equilibrium. So 100-hour fuels are basically 8-inch diameter pieces of wood is the rule of thumb. 1,000 hours are bigger than that, essentially. The Canadian system has the, I believe D is the DUF moisture code. It might be the drought moisture code. I always mix them up. The Palmer Drought Severity Index. And more recently, people have been looking at the evaporative demand drought index as an indicator for fire potential. I should also say energy release component from the National Fire Danger Rating System is used commonly, and because it uses a blend of the 1 hour, 10-hour, 1,000-hour, 100-hour fuels, it's not got a specific time memory. It depends on what fuel model you use in it. So that's a little bit of a muddling factor for purposes of this group, I suspect. And what I'm going to look at is, and what I've been looking at for my own work, is just how far in advance does the existence of drought indicate wildfire potential? How far ahead can we say we're in a drought now, so that'll affect fires coming up in a week, a month, 2 months? And what does the research today show on that question? So I'm going to start with Littell et al. 2009. They looked at total seasonal acres burned, or wildfire acres burned, WFAB. They broke the area into ecoregions, illustrated on the right, and the primary ones for our concern today listed on the left. They looked at 2 measures of moisture or drought. One was total precipitation, the other was Palmer Drought Severity Index. And each of those they looked at on 5 different time scales. They looked at annual, so I believe they started October for their annual, but it was a 1 year. They looked at winter, October through March. They looked at spring, March, April, May, and they looked at May through September as growing season, and then July through September as summer. And they tried to determine which of those measures, those 15 total measures, most correlated with seasonal acres burned. What they found, I'm going to hit the highlights here so I don't use up my time. What they found was primarily that over most of the region, the Sierra, the Northern Rockies, the Middle Rockies, it was a negative correlation between acres burned and summer Palmer Drought Severity Index. So negative because PDSI is negative when it's a drought. They also found that in the Intermountain semi-desert, the east side, basically, a large part of the east side of Washington and Oregon, that the previous winter, the previous spring, and the winter before that, 1 year ago at spring and 2 years ago winter, had an effect on the fire acres burned. precipitation is listed there too, but I wanted to stick mostly with the PDSI for my discussion with this group. Stavros et al. In 2014 asked the question of what factors, weather factors and climate factors, differentiate large fires over 1,000 acres from very large wildfires over 50,000 acres. Their unit of analysis spatially was Geographic Area Coordination Center based. So this part is, I'm going to focus on the Washington, Oregon piece of their results. I apologize to the rest of the group because I didn't understand that Idaho and Montana were at the party today. So Stavros et al. Will have results relevant to you. They are going to be slightly different from what I focus on. The weather measures that they looked at were monthly Palmer Drought Severity Index, 100-hour and 1,000-hour fuel moistures, that fuel blended energy release component, fine fuel moisture code, and Duff moisture code from the Canadian system. All of these they were looking at during the week of discovery of an individual fire. And just a point of reference, 1,000-hour fuels, 1,000 hours is about 42 days. So it's got a memory of something between 2 months and a month is the way I kind of think of it. Their results, the key point here was that it was the 1,000-hour fuel moisture that most closely corresponded, but it wasn't the 1,000-hour fuel moisture the week of discovery, it was the 1,000-hour fuel moisture 1 week later. There was a lag in that. And what that suggests is that it does have that the very large wildfires occur when you have a 40-ish day drought, but it's the later part of that 40 days that will be most impactful. So we're talking now we could guesstimate we're talking more like 30 days that have the most impact on differentiating when you get very large fires, 50,000 acres or more, versus just large fires. They also lowered that 50,000 acre threshold to 2 lower values, and when they did that, they found that the primary results were 100-hour fuel moistures for both of the lower thresholds. So if you go to smaller fires, you get more of an impact from the shorter term fuel moistures. Barbero et al. Was another project paper that came out of the same overall project that Stavros et al. Came out of. It was a joint fire science funded project. And in this case, the figure on the left shows the ecoregions that they used. The purple is Western Cordillera, and the yellow is cold desert. They looked at very large fires as distinct from large fires using a 90th percentile of all the database, which comes out to about 5,000 hectares, or I just pulled it up a minute ago, about 12,000 acres. You can also see on the right the seasonality of when these fires occur. So generally, large fires occur in July, August, September, and a few even in October. The upper graph shows that most of the very large fires started in July, August, September, with a shift to later fires a little bit to the east in the Idaho area. They again looked at discovery week conditions. So what were the conditions the day the fire started? They didn't have data available for each day after that, so they had, or what the actual burning duration of the fires were. So they focused on the discovery week conditions again. There's a list there of the drought measures that they used. And they found that basically for the Western Cordillera, it was the energy release component with its blend of fuel timescales and the Palmer Drought Severity Index for the month that were most relevant. And for the cold deserts, it was effective precipitation, which is precip adjusted for evapotranspiration, 30-day period, and PDSI that were important. Operationally, the Northwest Coordination Center in Portland has statistical models for the probability of a large fire start in each of these 12 climate regions. The regions are defined based on similarity of climate internally. They're called predictive service areas, PSAs. The Coordination Center models do not include any explicit drought indices like Palmer Drought Severity, but they do have some of the cumulative indices I've spoken of. So they have 10-hour and 100-hour fuel moistures and energy release component. They do not include 1,000-hour fuel moistures in the models. John Saltenberger in Portland does track those for a gut check, sort of a qualitative assessment. But what they found, what their statistical models found, was that the west side of the Cascades, as well as sort of discontinuously numbers 5, 9, and 11, all show a strong dependence on energy release component, whereas the other areas, 6, 7, 8, 10, and 12, so there's sort of this arc through the east side and down into southeastern Oregon, all depend on 100-hour fuel moistures more strongly than the others. I've got a paper that's in review right now, second round of review, that it looks at what I called fires of unusual size, or FOUSs, and my focus was on what is the impact of daily weather on daily fire growth. I looked at, sorry, set my alarm to stop when I hit 10 minutes. I was looking at pairs of fires. So there was a fire of unusual size, larger than 90,000 acres, and then there was a smaller but still very large fire between 25 and 75,000 acres. In looking at it, I used, even though I was focusing on daily weather, I also looked at 2 antecedent moisture measures. One was the sum of the hot, dry, windy index over the previous 10 days before the fire started, and which is hot, dry, windy is just wind speed times vapor pressure deficit. And the evaporative demand drought index, we looked at 1 week, 2 week, and 4 week calculated EDDI. And what we found was, first of all, that the 2 week EDDI, Eddie, was stronger than the 1 week or the 4 week in showing any distinction, but that the majority of the fires of unusual size had much higher EDDI values than their paired partner large fires. So this, any point on here represents a pair of an FOUS with a large fire. And looking at the daily data, what this showed was that basically the preceding dryness and drought essentially increased the efficiency of subsequent days of hot, dry winds for getting growth out of a fire. The bottom line out of what I've looked at in the existing literature is that total seasonal area appears largely sensitive to July, August, September Palmer Drought Severity Index. No ecoregion in that study showed a sensitivity to growing season PDSI. And to cut to the chase, shorter lead time indices appear to have a stronger influence on very large fire probability. That what we're seeing right now in terms of what the previous 2 speakers showed matters for any fires that may be burning in the next month or so, but makes less of a difference. So statistically, it didn't show up in these studies for any fires that aren't going and don't light up until August or September. That's not to say that the forecast of continuing drought into those months isn't significant and isn't meaningful, but the studies to date have shown that it's a shorter term lead up to fires in the Pacific Northwest that makes the most difference in what happens. And I will stop there.
Thank you very much, Brian. I will note that a few people are noting your Princess Bride reference there. Next, we will hear from John Abatsaglu about compound extremes driving the Western Oregon wildfires of September 2020. John, we see your climate-enabled slide. There we go. And I do not hear you, John. And we may be doing too many clicks of folks trying to unmute John. So John,
there we go.
There you are, okay.
There we are. I'm sorry, I did not see that mute button. So I'm gonna highlight basically the story from last year, last September, the end of Labor Day weekend, where we had the impressive fire siege across the Oregon Cascades. And this is a story that we do not hope repeats this year, but it ties in very much to some of the processes that previous speakers were talking about. And I'll highlight that Larry is one of the co-authors on this talk, and the current ridge that we have overhead right, we saw a similar ridge positioned a little bit offshore that was a catalyst for this event. So the big picture, right, is that we had a significant fire season last year, right? You can see some of the numbers here: 4% of the state of California, 1.5% of Oregon, the largest fire season in the modern era for the Western United States. And I'll also remind us that most of this fire activity really didn't get going until around mid-August. So much like as Brian was mentioning, right, things look really bad right now, and they could change, right? It could change for the worse, it could change for the better. So don't count the fire season out until it's basically over. A lot of impacts, of course, and what I want to focus in, of course, is the impacts here in Oregon. The Oregon Cascades, you can see how much fire occurred last year in 2020. More fire happened in 2020 in the Oregon Cascades than in the previous 36 years combined. It's about 11% of the Oregon Cascades burned in this fire, and most of that occurred over a short 3 to 4 day period, right? So I want to highlight essentially what happened in 2020 and talk about essentially a series of compound factors that really set this fire siege up. So 2020, of course, was a very warm and dry year, the year of the monsoon. You can take a look at sort of how elevated the vapor pressure deficit, another metric that might indicate potentially how dry conditions are, how available fuels are to burn. And the dark red here is basically saying that that is the highest vapor pressure deficit that we saw during this May through September period for much of the Southwest, getting up a little bit into parts of Oregon as well. And I'll remind you here that a little bit similar to what Brian was mentioning in the last talk, right? We have very strong links if we look at just the amount of area that burns in an individual year at a large scale, very strong links between the fire extent in forested environments and how dry the fire season is, measured through the fire danger indices, right? We call fuel aridity here. So that relationship is quite strong. It also is quite strong at sort of more regional levels as well, right? So that sort of enables, right, this sort of drought, or sort of drought enables fire activity. And another thing that also was happening, of course, right, leading up to the Labor Day fires, is that we had a lot of fire activity across the West. So yes, it was warm and dry in the Northwest, but in the grand scheme of things, there was a lot of action, right? And so the figure on the left here, this is September 6th, 2020. And what I'm showing you here on colored is basically the geographic area that is experiencing contemporaneous 95th percentile conditions in terms of a fire weather index, right? So widespread extreme fire danger across the West. The areas that are highlighted in dark red are forested environments. Something on the order of 85% of Western US forests were experiencing high fire danger at the same time. We had lots of fires going on across the Bay Area, California, much of sort of the Colorado Rockies as well. We had the wind turbine fires that, really ripped through parts of Washington state the day before. And so this really, this is another one of these examples of compound extremes. We had over 24,000 personnel assigned on fires. We had a national preparedness level of 5. That meant that resources were stretched thin. And then, of course, comes this incredible east wind event. Right, and so here's this east wind event that happened during that Labor Day weekend. Again, another sort of omega sort of blocking pattern, right? A little bit similar to what we have right now, but positioned off the coast. We had a strong cutoff low come across into the Four Corners region that brought some early season snowfall that didn't put the fire season to bed in the Colorado Rockies. And what we saw was a really strong northeast sea level pressure gradient, along with very strong easterly winds at around mountain pass level. So this here on the right is showing us those winds, right? And they're coming from the northeast, and the colors here are indicating that we had, the red color here is indicating that the winds are basically descending down the western slopes of the Cascades. And the combination of that, right, downslope winds, you get the air gets compressed, just like we're talking about with some of these mesoscale temperature extremes that we're seeing in Western Oregon and Western Washington today. The difference with this one is that we had a lot more, there was a lot more dynamics. The winds were quite a bit stronger. Okay, so what was notable about this wind event is that it resulted in some incredibly strong winds, and also it coincided with basically a period where the fuels were incredibly dry. So a lot of the stories of very large fires, it's not just that the fuels were dry, it's not just that there was ignition, it's also that there's some extreme critical fire weather event, and that fire weather event were these east winds, these east downslope winds. And we can see basically the vapor pressure deficit at some of these locations just did not recover at night. And so we had multiple days in a row where conditions were conducive to burning, and that accompanied with extremely strong winds resulted in really impressive rates of growth for many of these fires that spread down into some civilized parts of Western Oregon. The climate story, again, we had, if we look at sort of the summer as a whole, it wasn't, extreme by any nature, but if we look at sort of the latter half of summer, right, basically from July 15th leading up to that fire event, and we look at Western Oregon, right, we had this black dot here, and the individual red dots are showing individual years. So the way to interpret this is that it was incredibly dry and quite warm, right? The third or fourth warmest year on record and the third or fourth driest year on record for that time period. And when we look at some of the measures of cumulative fuel dryness, these buildup indices, like Brian mentioned before, we see that that energy release component continues to escalate and basically reaches a crescendo right here, coinciding with those really strong and dry offshore winds. And what we did was we did a couple things to basically test out how unusual this event was, right? We hadn't seen it before in the historical record. We looked at the combination of basically the strongest winds we've seen from the east using radiosonde records, as well as ground-based fuel measures like the energy release component. And when we combine those together, we find that the combination that we saw in terms of critically dry fuels and strong easterly winds we hadn't seen before in the observational records. So this was unprecedented in at least 40 years, right? We did this a couple different ways, one looking at just the combinations here, and then one using another fire danger index called the burning index, which gives us a potential, it relates to the flame lengths, and we found that those were essentially off the charts for this geography. Okay. And then finally, we wanted to just quickly contextualize this event relative to a series of very large fires that had occurred in Western Oregon, basically since the turn of the 20th century. And when we looked at all those fires, we found that the lion's share of them occurred when we had warm and dry summers, not necessarily the warmest and driest, but you can see here that most of them fall in this bottom right-hand quadrant, so warm, dry summers. And then most all of them occurred with some sort of easterly wind event, right? And so that sort of jives with a lot of conventional wisdom, but we provided some context here. And the number 13 is the Labor Day fires, right? What we found is that these fires occurred with the strongest easterly winds of any of these large fire complexes in the period of record. And so my quick summary here is that these fires were enabled by the warm and dry latter half of summer, enabled as well because we had simultaneous fires across the broader West and that limited fire suppression resources. The fire season extended a little bit later than it ought to, right? Usually you get some sort of fall precipitation that begins to cut into the fire threat. We didn't necessarily see that last year. And these fires, like many, right, it requires a number of things to happen, right? And so timing matters, situation matters, and we also contextualize that these compound extremes have a long history of driving big fires in the Northwest. And in the interest of time, I will end there.
Thank you very much, John. If folks have questions, you can put them in the question box. I realize we're at the top of the hour, so if you need to go, I understand. I will just try to take 1 or 2 questions that came in. First, going to Larry. What are the likely causes of the heat dome to form? Will these become more frequent as the climate warms? Are you able to respond to that, Larry?
I did, but I can real quick, I'll see if I can summarize it in maybe 2 sentences, 2 or 3 sentences. So basically that high pressure ridge that we showed in the earlier slides, so that's the heat dome. And so it's just a high pressure ridge that is driving offshore flow off of Oregon. And so there's some research that suggests that these ridges occur much more frequently when there is tropical cyclone activity in the Western Pacific. And that these tropical cyclones will set off these what are called Rossby waves. So essentially it just sets off some wave patterns that can influence the jet stream and make these high pressure ridges, heat domes, much more likely to occur. So as far as what to expect for the future, so a lot of climate model simulations and analysis of historical record has shown that these heat waves are increasing in frequency and intensity, and they're projected to continue doing so.
Thank you, Larry. 2 questions I'll combine together for John. How does the notion of compound extremes complicate climate attribution studies? And then related, what was the ignition cause for the Oregon fires?
Ooh, well, the latter one might get me in trouble. I will say that a couple of the fires were started with the same lightning bust that came through and started the fires in California in mid-August, and they sort of smoldered for a while. The first part, I think, yes, these are real interesting events because there's a strong dynamic driver, right? Namely this offshore wind event. And there's also the concept that we have, potentially climate change leading to much drier fuels that enables the fires to occur. So this is a sort of question that probably requires you to break down those individual drivers and view them in concert. And the story may be a little bit more complicated, although I think that there are people that are working on trying to tease that part of that out.
And I'll squeeze in 1 more question because I think the answer is short. What are the projections for the impacts on lightning starts due to these climate changes?
I can take a stab at that. So lightning ignitions, right, by themselves, we need to have dry fuels. And so with the warming and drying that we've seen, we tend to have higher what we call lightning ignition efficiency. If we have 100 strikes, maybe we'll see 3 or 4 of those materialize into fire. If it's wetter, there may only be 1 or 2. So that's my expectation, is that we'll tend to see more fires per strike. There's a bigger question about how the character of lightning may change, and I don't have a great answer to that. There are people that are sort of thinking about that general question now.
Okay, thank you. And there was clarification of more of the storms producing lightning, but as you're saying, we need to reach out to others for that. With that, I'd like to thank each of our speakers for their time, for their presentations. We really appreciate you sharing this information with everyone. Here are their emails if you want to follow up with any specific questions. And Britt Parker will be putting up a recording of this webinar later this week onto drought.gov. You'll receive an email about that, as well as the key highlights from the presentations. And if you have any questions or want to get a copy of the slides, you can email Britt Parker to get that information. And with that, don't forget, our next webinar is on the 23rd of August. I want to thank everybody for their time, and we look forward to connecting next time, and everybody try your best to stay hydrated and safe. Thank you very much.